Ladies and gentlemen, in the last classes we have seen the Gram-Schmidt procedure for the auto-chronalization of signals. Now we use this GS procedure for designing receivers. So we will see the concept of optimum detection in this video. So let me start with that presentation. The speech is organized in your learning outcomes, then about binary signaling and the probability of error in binary signaling. Then we will see the concept of maximum likelihood detection and the summary of understanding. In this video, you will learn the binary signaling and you will learn the block diagram of an optimum receiver. Then you will derive the probability of error for binary signaling. Then you will learn the maximum likelihood detection and you will derive the optimum threshold for maximum likelihood detection. So let us look at a baseband communication system that employs binary signaling. That is, a logic 0 is transmitted as a signal S1T and the logic 1 is transmitted as a signal S2T. So if during this symbol duration t, if it is a 0, you transmit a signal S1t, or you transmit, if it is a 1, you transmit a signal S2t. So in the receiver, the ambiguity is all about, it knows the signals S1t and S2t. The only ambiguity is which is coming now, whether it is a logic 0 that is corresponding to S1t, or is it a signal S2t corresponding to a logic 1. So these signals are passed through additive white Gaussian noise channel. Basically what we mean by baseband communication is this: the zeros and ones, the two logic levels, they are mapped onto two signals S1T and S2T, and they are transmitted as such, mostly as Gaussian pulses or as rectangular pulses or raised cosine pulses. Here there is no digital modulation, that is why it's called a baseband communication system. Something like our LAN systems, etc., short distance communications. So as it passes through the additive white Gaussian noise channel, some noise NT is added to that. So RT, the received signal, whatever is coming in the receiver, that is equal to SIT plus NT, whereas SIT can be either S1T or S2T. Now this SIT, it can be either S1T or S2T. The bits are mapped onto bits, or your digital signals, they are mapped onto your signals S1T and S2T, and they are transmitted here. This is my additive white Gaussian noise channel. Here it adds noise NT, and the resulting signal, the received signal here is SIT plus NT. Now at the receiver, there is a receiver filter. You know, in digital signal processing, any system is a filter in a system. Any discrete system is called a filter. And here I have a receiver filter. So this RT is convolved with my HT. So output of that is, so the output of the receiver filter is ZT, that is equal to RT convolution HT. Now this anti-convolution HT or ZT, these are sampled at every symbol duration, that at every t equal to nt, this is sampled. So it takes a value here, say that is Z of t, that is equal to AI TS plus NTS, where this is a single value here. Whatever I am getting here is a single value, that is AI plus NO, okay? Or it can be either A1 plus NO or A2 plus NO, depending on whether S1T or S2T is transmitted. So I get a value called ZI. It can have two values. So then a threshold is used to compare this. Say if it is a Z1, it is a S1T, or it is Z2, it is S2T. Some decision has to be made here. So then bits go out based on the value of this A, whether it is Z1 or Z2 corresponding to S1 or S2, some decision is made here. Now you can see that there is nothing, no uncertainty about this SIT is either S1T or S2T, but there is this NT is a Gaussian process. So this RT and consequently this ZT, they are Gaussian random variables. This random variable has a mean of AI, because it can be either A1 or A2. This is the mean of your signal S1T or S2T. and it has a variance 0, because I assume that this additive white Gaussian noise NT has a variance of 0. I said it's a 0 zero mean, no, not the variance, but the zero mean, because the variance of this, z is ai plus 0, because I assume that my noise nd is a zero mean Gaussian noise, so it is either a1 or a2, and so my z is a zero mean, is a has a mean ai, since n0 is a zero mean Gaussian random variable. Now, the threshold comparator, it checks two hypotheses: H1, that is S1T is transmitted, or H2, that is the hypothesis that S2T is transmitted. So if Z is greater than a certain threshold lambda, it makes a hypothesis that H1, that is S1T, is transmitted. If this value Z is less than some lambda, it makes a decision that a hypothesis H2, that is S2T, is transmitted. If Z equal to lambda, then the decision is arbitrary. Now that lambda, we have to compute the lambda, the optimum value of the threshold lambda. Now error happens when H1 is taken while S2T is transmitted, or when H2, the decision H2 or the hypothesis H2 is taken when S1T is transmitted. So the probability of error in this binary transmission P, that is probability of H2 given S1 into PS1, this conditional probability into this marginal probability, plus P H1 given S2 into PS2. Okay, you make these mistakes when you make the mistake when you take the hypothesis H2 when S1 is transmitted, or you take the hypothesis H1 when S2 is transmitted. And in most cases, you transmit a large number of bits. So PS1 equal to PS2 equal to half, because they are equiprobable in a long sequence of bits. So the probability of a 0 and a 1 are the same. So it is half. So PS1 equal to PS2 equal to half. So the probability of error P is half into PH2 given S1 plus PH1 given S2. Now, the maximum, now when we come to the maximum likelihood detection, here what we do is we maximize the ratio of likelihoods to find this threshold. So the threshold lambda is chosen to minimize the probability of error. Okay. So earlier we have seen the probability of error, the maximum likelihood detection, this method minimizes the probability of error. These are all optimum receivers. So what it optimizes here is the minimization of probability of error. Now let us consider a likelihood ratio lambda z, capital lambda z, that is equal to f z given s1 divided by f z given s2. What is my z? That is the output here. This is my z. Okay, this is my z value. When this ratio f z given s1 divided by f z given s2, this ratio is to be computed. If this is greater than PS2 by PS1, I take the hypothesis H1. If it is less than PS2 by PS1, I take the hypothesis H2. If you cross multiply here, you can see that you can easily verify this. Now this PS2 is equal to PS1, so this ratio becomes lambda z, that becomes Fz given S1 divided by Fz given S2. If it is greater than 1, I take the hypothesis H1. If it is less than 1, I take the hypothesis H2. Now if I cross multiply this equation, I can see that Fz given S1, if it is greater than Fz given S2, I take the hypothesis H1, that is S1 is transmitted. If it is less, I take the hypothesis H2, that is S2T is transmitted. Now you know that this Z is a Gaussian random variable with the mean given if Z given S1. This Gaussian random variable with the noise variance sigma n0 square and mean A1. Okay, so its PDF is 1 by root 2 pi sigma n0 square e raised to minus of Z minus A1 whole square by 2 sigma n0 square. Because this has a mean of A1, because Z has a mean of A1, given S1 it has a mean of A1, and it has a noise, it has a variance of sigma n 0 square. So likewise, f z given s2, that is 1 by root 2 pi sigma n o square, e raised to minus z minus a2 whole square by 2 sigma n o square, because it has a mean of a2. That my noise, my AW region has 0 mean. So this mean f z given s2 has a mean of a2. Now, if I take the ratio, this constant factor 1 by root 2 pi sigma n o square is cancelled. So it is e raised to minus z minus a1 whole square by 2 sigma square divided by e raised to minus z minus a2 whole square by 2 sigma square. So it is e raised to minus z minus a1 whole square plus z minus a2 whole square by 2 sigma square. Now on expansion, I can take the logarithm of this thing. Now this lambda is this ratio should be greater than or less than 1. So if I take the log on left side and right side, it becomes logarithm of this one, it becomes this factor, that is z minus a2 whole square minus z minus a1 whole square by 2 sigma square, that is greater than or equal to log 1. So when I expand this equation, you can see that z square is cancelled off. Then I have a 2 z into a1 minus a2 by 2 sigma square. So that becomes a1 minus a2z by sigma square, because the 2 is cancelled by this 2z. Then I have the last term, that is a2 square minus a1 square. I'm sorry, a1 square minus a2 square, because this a1 square minus a2 square minus a1 square minus a2 square divided by 2 sigma square is greater than or equal to less than log 1. This log 1 is a 0. So I can cancel off this a1 minus a2. This sigma n square I can cancel off. a1 minus a2 I can cancel off. So what comes here is z. Z is greater than or equal to a1 plus a2 by 2. So if z is greater than a1 plus a2 by 2, I take the hypothesis h1. If it is less than a1 plus a2 by 2, I take the hypothesis h2. So the optimum threshold in this case is lambda 0, that is a1 plus a2 by 2. That is the average of the means of s1 and s2, s1t and s2t. If it is midway between, if this optimum threshold is midway between the means of s1t and s2t. If it is below a1 plus a2 by 2, I say s1t is transmitted. If it is greater than a1 plus a2 by 2, whatever measured at the receiver or the sampler, if it is greater than a1 plus a2 by 2, I take the decision h1, that is s1t is transmitted. If it is less than that value, I make the decision that s2t is transmitted. Now in this video you understood the binary signaling, then you learned the block diagram of an optimum receiver, a general block diagram of an optimum receiver, then you derived the probability of error for binary signaling, then you understood the maximum likelihood detection, then you derived the optimum threshold for maximum likelihood detection. And that is the end of this